Hello, welcome back. So in this video, we are going to start the coding for the OLED controller. So remember in the last video when we discussed the architecture of the OLED, we have seen like it communicates with the Zinc chip through the SPI controller. Now we have already used an SPI controller. We have actually designed an SPI controller in the previous tutorial. So we are going to reuse that SPI controller to build the complete OLED display. Okay, so I am going to start it as a new project. Before that, this was the code for SPI controller. We are going to reuse it. So what I'll do is I will go ahead and remove this keep attribute, which we use for debugging purpose to see the internal signals. But the issue with keep attribute is it will prevent Vivado from optimization. So we don't want that to happen. So removing the attribute so that Vivado is free to optimize whatever variable he wants to. Okay. So I'm going to file and start a new project. And I'm going to call it OLED control and RTL project. And here, so in all our previous project, we used to skip this screen because we didn't have already built code. But in this case, that's not the case. We already have the code for SPI controller and we can reuse it. Okay, so what I'm going to do is I'm going to add the code for SPI controller to my new project. So we'll go to add files and you need to know where the source codes are stored actually. So any Vivado project you take, inside that one important file is this .xpr file, which is the Xilinx project file or the Vivado project file. And another important folder is this one, the project name .sources folder, where all your source codes will be saved. Okay, so if you want to share your project with someone else, the only two folders that you need to share are this xpr file as well as the .sources folder. All other folders are temporary, so you don't have to share it with other people. These two are enough actually. So let me go inside .sources. You will see two folders, sources_1. If you go inside that, you will see your Vivado code, and there is constraints_1. If you go inside that, you will see the XDC file, the constraints file. Okay, so this is where by default all source codes are stored, and these are the names by default, sources_1 and constraints_1. Of course, you can change it the default name, but these are the default names. So I'll go to my SPI control project folder. I will go inside sources. I will go inside sources1 and I will choose this SPI control. And remember to check this option, copy sources to project. If you don't check it, okay, this original source file will not be copied to your new project. Okay, the new project will be using the file in the other project. So in case if you are modifying this file in the new project, it will reflect in the old project also, which you may not want to happen. So if you check this option, he will take a copy of that folder, copy of that file and put it in the .sources folder of your new project. So remember to check it. By default, it is not checked, so remember to check it. Okay, and here again you can add the constraint file if you already have. We have a constraint file for SPI controller, but most of the pin constraints there are not valid for our OLED control, so I'm not adding it. I'll just click next and I'll choose Zedboard as my target board and finish. Yes. Now if you forget to add files when you create a new project, of course you can add it later by choosing add sources and add or create design sources, and by choosing add files instead of create file, you will get the same window and you can go ahead and add the existing source file to your project, no problem. Okay, so this is our project and we already have SPI controller here. Currently that is the top file. Now I'm going to create a new file. So again we are going to do hierarchical design. So I'm going to call the top module as OLED controller, and he will be instantiating the SPI controller inside that. Okay, so I'm going to create a new file and going to call it OLED control.v. And again, you can see the option here, local to project. If you choose local to project, he will store this file in the .sources folder of your current project, or you can change it and save the file at some other location. But preferably, we always keep all the files in the local project folder. Okay, finish. Okay, and OLED control comes here. And first thing I'm going to do is declare the input output for the OLED. Now, in order to do that, I'll look at the Z data sheet and see which all pins are connected between zinc and the OLED display. So you'll see wherever you can see the pin number, that means those pins are connected. Wherever you see not connected, that means that is not connected to zinc, but it is actually managed on the PCB itself. So you don't have to do anything to these pins from zinc. Okay, so I'm going to write the input output. So let me write it, OLED interface as a command. So OLED, I have SPI clock. So I am prefixing OLED with everything to indicate these signals are interface with the OLED. Okay. Now we have SPI clock, we have OLED SPI data. We also have output OLED VDD. We have output OLED VBAT. We have output OLED reset underscore n. I am putting a postfix underscore n to indicate this is a active low signal. That means if you want to reset the OLED controller, you need to make the signal low. A normal operation, this signal will be high. Now output OLED underscore DC underscore. Again, remember this signal is used to choose between whether you are sending data through SPI interface or you are sending some command through the SPI interface. So that is the signal. That's it. So these are the signals going to our OLED. Now, in addition to that, we need an input clock. This is our 200 megahertz, right? No, 100 megahertz. 100 megahertz onboard clock is coming, and we also have the reset signal. So we'll assign this reset to one of the push buttons and use it. Whether output should be reg type or y type, we will see it while we are doing the code. Okay, so this makes the basic input output interface. Now, first thing I'm going to do is I'm directly going to instantiate my SPI controller inside the OLED controller. So I'll go ahead and take the interface for SPI controller and put it here, and I will do the port mapping. So I'll call SPI controller, maybe SC as the instance name, and do the port mapping. So some of the signals you can readily connect. For example, this clock is the input 100 megahertz. We already have it coming from top, so you can just go ahead and connect here. You also have the reset coming from the top. You can go ahead and connect that. We have SPI clock, which is the output clock to SPI, 10 megahertz, which is this one. So I can directly connect there. And we have SPI data, which is this one, so we can connect it there. So since these signals are connected to the output port of an instance, they should be wire type, so no need to change them. They remain wire type, or you can explicitly say output wire, or just leave it blank. Perfect. Now other signal, data in, load data, done send. Those signals are currently not available, so these signals should be generated within the module and interface with the SPI controller. So whenever we want to send some data, we'll put that data here, we'll make the signal high, and we will wait until this signal goes high. That means that data has been sent through the SPI interface. Fine. Now in the slides, okay, we have seen that you have to send a specific sequence when the system starts up so that the OLED controller is initialized. And that is what we are going to do next. Now you'll see this sequence follows a particular order, right? First you need to make the signal high, then wait for this thing, wait for this thing. So the best way to implement this logic is through a state machine. So we are going to write a state machine following the standard way of writing state machines in Verilog, and that state machine will initialize our OLED control. So that's what we are going to do. Again, I'm not declaring any signal at this point of time. We will add the signal as we go along, as required. Okay, so I'm just declaring always at post such, let's say clock begin end, if reset begin end. Okay, so every statement when you reset, it should go to a non-state. So I'm going to use a register called state to store my current state, and I'm saying when I power up, I'll be in the idle state. Now you need to declare all these registers as well as this local parameter. So we will declare it towards the end, because if I want to know what should be the size of the state, which is basically a bunch of flip-flops which will store the current state of the system, I need to know how many states are there, so that it will be log to the base of 2 number of states. So at this point I really don't know how many states are there. So we will add the states and finally find out how many states are there, then we will declare state. Okay, anyway, we'll have to declare it at some point of time, the size. And okay, reg state, I'm just declaring it, and the size we will change as we go along. And idle, we usually declare it as a local param, and idle equal to tick d 0. Again, I am not specifying what is the size of this constant, because I don't know at this point what is the size, but it will perfectly fine. This will also work, okay, as long as the number of states is less than 2 to the power of 31 minus 1. Okay, so on reset we are in idle state, and along with that we need to initialize some of other data also. For example, the signals to the OLED controller. When we start, what should be these signal values? Fine. So I'm going to say OLED VDD is 1. So from where I'm getting this information? All these are coming from the data sheet. Okay, VDD is 1. And what is VDD and all is given here. This is power supply for logic. So we are making it high at the beginning. And since I'm using it inside always block, so of course it should be reg type. Now you will see all the signals we are going to use inside the state machine, inside the always block. So essentially all of them should be reg type. So VDD is 1. Now OLED VBAT is also 1. OLED reset is 1. I'm not making it under reset. I'm not applying reset to OLED at this point of time. And OLED DC underscore N is also 1. It really doesn't matter. It can be 1 or 0 at the beginning. That's it. Okay. So this much I am going to do when I press the reset button. There is something wrong here. Let's see. OLED reset underscore N. Okay, it is reset underscore N. Now, if there is no reset, else begin end, we write the state machine. So we use the case state, and case. So remember to put indentation so that your code is readable. So we are in idle state, and let's look what is the initialization sequence. So I am in idle state, and as soon as I remove the reset, what I'm going to do is I'm going to initialize the OLED controller by sending this particular sequence that we discussed. Okay, so in order to do that, what I'm doing is so what is our sequence? We need to apply reset and make VBAT equal to 1. Okay, that's what we need to do. So let's take VBAT. It is already 1, but still for completion let me make it 1 again, but it will be already 1 when you come to idle state. Okay, VBAT is 1. Again, reset also 1. So reset is also 1. Now other signal again, if you prefer you can change them. So DC I am going to make it 0 because I'm going to send a bunch of commands actually. So I need to send a bunch of commands before I can write to the display RAM. Okay, so DC, reset, VPAT and VDD. I'm going to make it 0 because VDD is what? Power supply to logic. So it's interesting, this signal is actually active low. Okay, it's not active high. If you want to apply power, the signal has to be made active low. That depends upon how it is connected on the PCB. Again, I'm getting the information by reading the datasheet. Okay, so this much is done. And idle state. So we have done this part. Apply reset, make VBAT equal to 1. Apply reset. Oh, we didn't apply the reset. It should be active low. So I need to correct this. Remove reset and make VBAT equal to 1. Okay. So reset should be 1 here. My mistake. Anyway, we'll make reset low after 2 nanoseconds. So now what I need is I need to wait for 2 milliseconds. Okay, so there should be some circuit which generates 2 millisecond delay. So we have already seen circuits to create delay. So we are going to make a circuit which will give me 2 millisecond delay. Okay, that's what I'm going to do next. So I will call it delay gen.v or something. Okay. And this is how we do. We'll use a counter, and remember this guy is also going to run at 100 megahertz. Okay, and we need to find the counter value so that when that counter value reaches, we have 100 megahertz delay. Okay, that's the basic logic we are going to use. Okay, so he gets a clock, and whenever you need a delay, you will make this particular signal high, delay enable high. So you're basically telling the delay generator enable the delay generation. I want to get the delay, and if you're done, you'll have an output signal, output red it will be, which will basically say he has generated that much delay. Okay, so all these interfaces you will see between modules, there is some kind of handshaking happening. One module will be asking another module to do something by using some enable signal or valid signal, and the other module will tell this module I have done by sending a done signal or ready signal, something like that. So this style we call as a producer consumer model, which is a very popular handshaking methods when we go for VLSI design. Okay, so of course we need a counter, and what should be counter value? We can see our clock is 100 megahertz, so period is 100 kilo mega. Okay, store it in memory, and we need 2 millisecond delay. 2 divided by 1000 divided by memory. Okay, so my counter should be able to count till 200,000. How big should be my counter? Let's see. I need 200,000. This is in binary. 18, right? 18. So I'll say 17 down to 0 count. Now how the counter will work? So I'll say always at postage clock begin. If someone asks me to create the delay and this counter not equal to 1 2 3 4 5, what I will do is I will increment the counter. Else, that means if the signal is low or if the counter is not this value. Okay, if it is less than this value or more than this value, doesn't matter, I will make counter back to 0. Will it become more than this value? No, this will not become more than this value because this condition won't be satisfied once it reaches this value. Okay, so it won't go to this condition so it will stay at this particular value. Now we need to generate this delay done signal. So what I'm doing is always set again for such clock begin if, and this condition I will take delay enable, and counter when it reaches this particular value. Okay, I will make delay done as high, basically saying I have generated this much delay, B1. Else, that means if the signal is low, if the counter value is not this one, I will make this signal low. So basically what is going to happen, if you want to create 2 milliseconds delay, you will make this signal high and you will wait for this signal to go high. So when this signal high, the counter will keep on incrementing. At some point it will reach this particular value, this signal will go high, and once you see this signal is high, you will make this signal low, so that counter goes back to 0, which will make delay done go back to 0. Okay, so this is what we call as a producer consumer model of handshake. Okay, so I'm going to take this generator and I'm going to instantiate that also under my OLED control. Delay gen, let's call it DG. Again, we need to do port mapping. So clock, delay enable, and delay done. I'm going to connect the 100 MHz clock here. And this signal, okay, let me call it something like start delay. So this signal should come from your state machine, and maybe we can call it delay done itself, whatever name you prefer. Okay, so we need to declare them. If you don't declare them, Vivado will show them in blue. Okay, so remember to declare. So let me take them and go to the top. Start delay is coming from the state machine, that is inside an always block, so of course it should be a reg type. And delay done is an output from a module, that means it should be wire type. Okay, looks fair. Let's come back to our state machine. So I did this much. Now what I need is I need to create this 2 millisecond delay. So what I'll do is I'll create a state called delay state, and in the next clock I will switch to that delay state. Okay, so let's write the delay state. So delay will be also a local pattern. So let me write it here. Delay equal to 1. So here what am I going to do? I will make this signal high, start delay. I'm going to make it high. Now you need to initialize that signal also under reset. So when I press reset, I'll make sure you need to make all the registers inside a state machine to some default value under reset condition. Okay, so remember to do that. So it is 0, okay, 0 under reset, and when I come to this state, I am making that signal high, and I will stay in this state until this delay done comes. Okay, delay done comes means 2 millisecond has elapsed. I can go to the next state. Okay, so next state, let me call it something called init state. You can give whatever name you want. Now we need to declare init also. Okay, init equal to d2. Okay, init. What we should do next? Wait for 2 milliseconds. We have to send this particular command. Send display off command that we need to send through the SPI interface. Okay, so that's what we are going to do next. So what we should do, we need to send that command AE through this SPI interface. Okay, so what I'm going to write is SPI data is HAE Now remember the SPI controller, how he works. So he needs to get the data here, and he needs to see this signal going high, then only he will start sending. Okay, so that signal is here. Okay, so we need to connect all the signals here. So SPI data, I'm going to connect to data in, and it should be declared that is 8-bit wide, so 700 SPI data. And under reset, initializing data is optional, but it is mandatory to initialize all control signal. But let's initialize to 0 under reset. So SPI data becomes AE. Now other signal is, let me call it SPI load data B1, which will basically tell the SPI controller this one, load data. Okay, new data is available for transmission. So this signal I should connect here, and we need to declare it also inside Statemachine, so rich type, and initialize to 0. Okay, so we made this signal high, and it will remain in this state until the SPI controller says he has finished sending. Okay, how he sends it? Through this done signal. So let me call this as SPI done, and let's declare it. It's output from a module, so I need to declare it as wire type, and we'll say if this signal goes high, we'll go to next state, and if the signal is not high, we are going to remain in the same state. Okay, we are waiting for the SPI controller to send the data. Okay, once he sends, this signal goes high. Now remember the complete SPI protocol. So he will look at this data. Where is the state machine? Here he will look at this data, he will start sending, and finally he is coming to this done state, and he will remain in the done state until the load data becomes low. So what we'll do is, here I will say SPI load data is 0, and let's say what we are supposed to do next. So in the sequence we have finished this much, and we need to remove the reset actually. So we'll say OLED RST underscore n 0, and then we have to wait for again 2 milliseconds. Okay, now we already have a state here, which will wait for 2 milliseconds, but the problem here is from this state we'll always go to the init state. Okay, so we will be stuck in a loop. Like if I just write like state is, let's say delay, just like that. So from here I will go to delay, and I will wait for 2 milliseconds. I will come back here again, I will go back here. That's the problem. So one way to avoid this is you can create another state, maybe called delay 1, and copy paste the exact code here and call it delay 1. This is one way to do it, but it's not very efficient. So if you see, we need 2 milliseconds here also, so we will have to create another delay state there also. So this is one common scenario which we will face when writing state machine. Okay, so let me take a general case and try to explain that. So suppose you have a state machine, we have, let's say, states S1, S2, S3, S4, and from S1 you want to go to S2, from S2 you want to go to S3, from S3 you want to go back to S2, and if you are coming to S2 from S3, next time you want to go to S4. Okay, so this is the similar scenario. So under this, what you'll have to do is you need some indication, some kind of a flag to indicate from which state you came to S2, so that you can decide from S2 to which state you should go. Okay, so I will show you a simple technique how we will do. Okay, so I'm creating another register called something like next state. So next state, what I will put in next state is to which state I should go once I go to the delay state. Okay, for example, here we have state delay, and here also I will say next state is okay. So I'm going to delay. From delay, where should I go? I will say init. Instead of init here, I'll just write next state. See, so from idle, I'm going to delay, but I have stored this information here. Next state is init, and I will come to delay. Once delay done, state will be next state. So what is the value here? Init. So I will go to init. Now in init, what I will do is next state, where I want to go. I want to go for this remove reset. Okay, so I will just say reset. Okay, so if I go to delay from idle state, from delay state, I will go to init state. From init state, when I go to delay state, next state will be so-called the reset state. So we'll declare all of them. OLED. Okay, I think it's called reset underscore n. So we'll declare this state also. Okay, reset equal to dt3. Or you can make another variable called previous state also, which will indicate from which state you came to delay state, and here you can check if previous state is so and so, state is so and so. Okay, so you will have a if else if or another case statement under the delay state to decide to which state you should go from the delay state based on from which state you came to the delay state. So we need to declare next state also. Again, the size of next state will be same as state, which we will decide at the end. And let's initialize next state also to idle state. Really doesn't matter whether you initialize this one, but let's initialize to idle state. Okay, so we are in reset state, and what I'll do is I will remove the reset actually. Reset equal to 1. And after this, I have to again delay for 2 milliseconds. So I think in the slide, I forgot to put this condition here. Wait for 2 milliseconds here also we need. Okay, that's the thing. So from this state, I have to again go to the delay state. So same technique we will use. So we will have state equal to delay, and from delay we need to go to so-called charge pump configuration. Okay, so we will call it charge pump or something. We'll declare a state. So I'll go back to delay state, and again I will come back to charge pump. Okay, so now we are in charge pump. What I basically have to do is send a command over SPI, so it will look again exactly like this. But which command you need to send? It is 8D. Okay, there are two values. This is a command, and this is a value for so-called the charge pump. So you need to send two values through two SPI transactions. So this I will say 8D, load SPI. If SPI done, load SPI 0, load data 0. Okay, so here there is no reset thing. We are done with reset thing. We have to just decide which is the next state. Okay, there's no delay after that, so you don't have to use the next state under this one, so it's fine. Okay, now here is our next problem. Okay, the problem is our SPI controller, it is running at 10 megahertz, and our OLED control, this state machine, is running at 100 megahertz. So if you make SPI load data equal to 0 here, and if you go to the next state, the problem is by the time you reach the next state, the SPI control, he won't see the signal because he is running at 1/10th of the clock frequency at which this state machine is running. Okay, so that's the problem. That issue is there here also, but it's okay here because from here you are going to a delay state and you are waiting for like 2 milliseconds. By that time he will definitely see it. Okay, but here that is not the case. From this charge pump you send 8D, next you have to send 14 0x14 through SPI. Okay, that is the next state. So as I mentioned before, the problem is this state machine, he is stuck at this done state until he sees the load data equal to 0. Now this signal, you are making it 0, but by the time you go to the next state, he won't see it because his frequency is 1/10th of this one. So we need a special state. Let me call it wait SPI, and I will wait in that state until the SPI controller sees the signal. How do I know whether he saw the signal? As soon as he sees the signal, he will make this signal low. So that's how I am going to find out whether the SPI controller really saw this load data equal to 0 signal. Okay, so what I will do is wait SPI, and I will write if not SPI done. I think that is the signal. SPI done. That means this signal became 0. That means he actually saw the signal equals to 0. Okay, so where we have to go? We have to go to next step, which is basically again sending some data through SPI 14. Okay, so let me call it state is charge pump. Okay, let's call it charge pump 1 or something. Charge pump 1. So let's declare it here, 55, and code is more or less exactly same. Charge pump, charge pump 1. Okay, charge pump 1, and SPI data is this time 14. Tick H 14. SPI load data done. SPI load 0. Okay, so same issue here also, same as our delay thing. So after this state also, I need to go and wait for SPI to make this signal equal to low. So if I just write like this, he will come back here, he will come back here, he will come back here, he will come back here. So it's in an infinite loop. Okay, so here also what I will do is state equal to next state I will write. Okay, next state I will write, and here what I should write, I should write next state is charge pump 1, charge pump 1. So that from here he comes here, from here he goes here. And here I will again type next state is okay. After charge pump, I have to configure so-called the pre-charge. So let me call pre-charge. Wait SPI not declared. Okay, so we will declare wait SPI. Wait SPI, tick D6. You also have a new state, pre-charge. Okay, tick D7. Charge pump 1 not declared. Oh, so there are some spelling mistake. Charge pump 1. This is okay, so let's make this also for uniform. Okay, so now you repeat the same thing. So I can copy paste this. Instead of charge pump, this is pre-charge. In pre-charge, we are going to send D9 SPI load SPI data. After that, I have to send F1. So I am going to call it pre-charge 1. So we'll have pre-charge 1 here, and we are going to send F1 there. And after that, VBAT equal to 0. Okay, so let's call it next state is VBAT on, and there we say VBAT on, and there we'll say OLED VBAT is 1. And after that, again wait for 2 milliseconds. So same technique, state is delay, and you also have to say next state, so that from delay he will go to the correct state. So after we wait for 2 milliseconds, set contrast. Okay, so let me call the next state contrast. Okay, now we have to declare all of them. Pre-charge 1, 8, VBAT on, and contrast. N and contrast. Done. Okay, so in contrast, again same SPI transaction 81 and FF. So let's say this is contrast. Let's say 81. We'll go to contrast 1, and contrast 1, make it FF. Then something called segment remap. Again, you need to send this value A0. Okay, let's say seg remap or something, and there we'll say A0. this sec remap. Be very careful when you copy paste actually. And from segment remap, we are setting the scan direction. So let's call it something like scan direction, and we need to send C0. Okay, C0. Scan direction, we are setting comp pin, so let's call it comp pin, and the data is second sec remap C0. I think I messed up somewhere. Contrast FF sec remap. This A0 actually is A0. Then scan direction is C0. Okay, that one is correct. Now we have the comp pin. There it is. DA. Let's call it comp pin 1. Next one. 0 0. Now display on. AF. Okay, now we have to declare all these things. So contrast 1 and sec remap. Okay, contrast 1 sec map. Scan direction comp pin 1. This should be comp pin 1. Okay, so we have scan direction 13. Control D is the shortcut to duplicate a line. Vivado, so you can use that. Scan direction, I think there is only one, I guess. Scan direction, yeah, there is only one. Comp pin and comp pin 1. Comp pin 1. And finally, it was something called the display on. Okay, so we are more or less done with the state machine for initialization. Now, how do we know whether the initialization is right or not? One way is to send some data and see whether it is coming on the OLED. Another easiest way is we can send a special command which will turn on all the pixels on the OLED. Okay, so that's what I am going to try now. So I will send a special command. It is A5, and if that command is sent, it will turn on every pixel on the OLED. So we'll see whether that is working or not. Okay, so let's again copy paste the same thing, and I am just writing something like full display or something, and it is A5, and let me say next state is something called done, and I am stuck at this done. So in this video I am doing only till the initialization part. So what I'll do is I'll keep my state machine in the done state forever once it reaches done state. And in the next video we will continue with the state machine and add the states for sending data to the display. Full display and done. So 14, 15, 16, 17, 18. So we have 18 state as of now. Now to encode 18 state we need 5 bits minimum. So this state machine I will declare 4 down to 0. Same way next state also I will declare 4 down to 0. Okay. Let's quickly go through the code once again. Okay, here I can see some copy paste issue. So from display, next state I have written display, so we are stuck actually here. It should have been okay, full display. Okay, please correct it. Now let's simulate and see whether things are working as expected. Now in this project you have multiple modules. Okay, now which module should be implemented, we usually choose by right click and say set as top, and currently OLED control is our top module, so this is the one which will be implemented when we run synthesis and implementation. Now for simulation, this is not how you choose which module should be simulated. If you have many modules in the same project, you should go to settings and simulation here, and here you can choose which is the top module for simulation. Anyway, now it is OLED control. Now if you want to simulate our SPI controller, you have to, I don't know, what was the name, I don't remember. Okay, SPI control. Okay, so we have to change this to SPI control and it will simulate SPI control. Okay, now it will simulate SPI controller actually. Okay, this is how we choose. Okay, let me change it back to OLED control. Okay, and run simulation, behavioral simulation. Okay, these are our top level signals from OLED control. If you want to see the signals in the sub modules, you can add them to the waveform. So what we usually do is right click and say new divider and say delay generator, and I click the delay generator here, right click and add to wave. So all the waves from delay generator comes here. New divider, let's call it SPI controller something, and right click SPI controller. It is showing the instance names here, okay, not the module name. These are the instance names we used, DG and SC. So right click and say add to it. Fine, so let's restart and clock, force clock 0 1 10 nanosecond. Reset, let's force constant. Apply reset for some time. Okay, now let's remove the reset force constant 1. Okay, force constant of 1 0. Okay, now reset is gone. Now the state should be changing. So we were in 0, I think idle state. We came to 1, which is state 1 is the delay state, and we are somehow stuck at delay state. No, it is 2 millisecond delay. Okay, so we'll put 1 more second. Yeah, okay, so we came to the delay state, then we went to state 3, which is the reset one. Okay, OLED SPI clock. So here something is happening. Some data is sent to the OLED in state 2. So what would we write in state 2? Init state. So in init state we are sending AE, and remember we are sending the MS bit first. So this is 10101110, which is AE. So that is correct actually. And let's keep on running. So state is, we are back in some delay state on 3, so we had to wait till 4, I guess. Yeah, it is working. This is one issue I can see is this delay enable is always stuck at 1 in the delay generator. See that? This was our counter. So it reached 200, delay done went high, and because of the logic, the way we have written, the counter is going back to 0 and again starting from 1. But the protocol what we wanted to implement was this will go high, then delay enable will go low actually. That's why he became as this 200,000 and immediately starting counting again, because this is constantly stuck at 1. So where is our delay state? Here. So we made the start delay high here, and once delay done, we forgot to make it back to 0. So we need to do that. Okay. Only other issue that I find is the VDD is constantly stuck at no, VDD is fine. VBAT is somehow constantly stuck 1. VBAT is an active low signal, so that also we need to correct here. VBAT, okay, so we need to make it 0. Otherwise everything looks fine. State machine goes till 18, which is the last state, and it remains in state 18. Now once you are done with simulation, you can go ahead and do synthesis. After synthesis you have to do pin assignment. I have already done it in the background. So you need to look at the datasheet, Zedboard, and see where each pin is connected to the zinc chip, and you do the XDC file and the clock constraint. After that you go ahead and do implementation and generate bit stream. Once you generate bit stream, we will program. Okay, so you need to do everything. I have already done it. Program device and program. Once you program, this is how the OLED should look like. Okay, all the pixels are turned on because of our last command, A5 command. So if I press reset, it will become dim, and once I release, all pixels turns on. Okay, so that's all in this video. In the next video we will continue, so we will remove this full display and done, maybe full display from here, and expand the state machine so that we can send some string to the OLED and see it there. Thank you.